Our next speaker is Ruth Luo, who will be talking about extensions of a theorem of Erdős on non-Hamiltonian graphs. Ruth, take it away.
Okay, thanks Luke. Thanks to the organizers for allowing me to speak. Today I'm talking about some extremal problems, and these are all joint work with Zoltan Ferretti and my advisor Alexander Kostochka. Okay, so let's just talk about Hamiltonicity. A graph is Hamiltonian if we have some cycle that covers every vertex in the graph. It's non-Hamiltonian if we don't have such a cycle. And so let's define this function first, this h and x function. So n minus x choose 2 plus x squared. The first Turon type result for Hamiltonicity was due to Ora in 1959. He proved that if we have an n-vertex graph and the number of edges is greater than hn1, then G is Hamiltonian with this extremal example. So here we have a large clique, order n-1, and we have just one vertex with degree 1. So you can count the edges here. We have n-1 choose 2 plus 1 squared. So exactly hn1. And it's non-Hamiltonian because we have this vertex of degree 1. So if we had some Hamiltonian cycle, every vertex in it needs to have degree at least 2. So naturally, we might want to avoid vertices of degree 1, see if we can get a better bound. So a couple years later, Erdős proved this extension of Orr's result. So, okay, fix a graph G with minimum degree at least some prescribed D. So D should be at least 2 for this problem to be interesting. And then if the number of edges is greater than the maximum of that quantity, then G is Hamiltonian. Okay, and so let's just look at the proof. Actually, I thought I would run out of time, so I cut out every single other proof, so this is the only one. Okay, so the proof, we're going to use another classical theorem for Hamiltonian graphs due to Posha, which says that if for every k from 1 to floor of n-1 over 2, the number of vertices with degree at most k is strictly less than k, then G is Hamiltonian. So we don't want a lot of vertices with small degree. So let's suppose the graph that we have is non-Hamiltonian, so we want to use the contrapositive of Posha's theorem. So we have some value k, at most floor of n-1 over 2, such that G contains some set, call it D, of k vertices with degree at most k. And so to satisfy our minimum degree condition, we should have k to be at least our minimum degree, which is at least k. And then we just count the number of edges. So in G minus the set D, we have n minus k choose 2 at most. And then for edges incident to D, so we have k vertices in there. They each have degree at most k, so we have this k-squared factor. Altogether, this is h and k. And then the theorem just follows by convexity of the function h and k. So it is convex. I mean, it's a parabola. And so this function attains its maximum at one of the endpoints. So it's either this k, this floor of n-1 over 2, or d. So that's how we get this bound. Okay. So just a simple theorem. And from this proof, we can kind of guess what the extremal examples are going to be. So let's define this class of graphs, the same wave graphs, h and d. So fix n, fix d. This graph has a large clique of order n minus d, and then an independent set here of size d, such that every vertex there has the same d neighbors within the big clique. So here we have complete bipartite. Okay, right, so 2 observations. It's non-Hamiltonian, and here I have a version with all the edges drawn in. So we can tell it's non-Hamiltonian because over here, if we had a cycle that included these vertices, we need to go through these d in the middle, and kind of the best we can do is just go back and forth here, but then we run out of vertices in the middle. So we can't find a spanning cycle, and so you can check that the number of edges is exactly this function little h and d. So these are our extremal examples. Okay, So something that has become popular kind of lately is, so we forbid some graph. Instead of just counting number of edges, we count the number of, say, triangles, cliques, cycles, some other subgraphs. So, okay, fixed two graphs, t and h. Let's define this function, x and th, to be the maximum number of copies of t in an h-free graph. And here, so different from the other talks earlier, we don't care if t is induced or not. Same for h, so just some copy. And so when t is equal to k2, so we want to count the maximum number of copies of k2, so edges, in an h-free graph. That's just the regular extremal function that we know. So this is some generalization of the extremal function. Okay, the notation was first introduced, this x and th, recently actually, by Alon and Schickelman in, I think, a 2016 paper called Many T Copies in H-Free Graphs. So within this paper, they have a number of different results. Here are some examples. So the first one, they counted the maximum number of copies of triangles in graphs without C5. So they gave an upper bound here, which is this some order n to the 3/2. And so you may recall, or not, but this n to the 3/2 is the same order as the extremal number of C4. So the maximum number of edges in a C4 free graph. So these problems are actually quite related. And kind of, well, unrelated to that, so when t and h are any tree that you want, they determined x and th, or at least the order of growth exactly. And so that depends on some parameters, which are kind of too complicated to explain right now. Okay, and many other nice results. Okay, but even though this notation was only recently introduced, I mean, this is not a new problem. There have been many different results for different combinations of t and h's. The first was due to Erdős in 1962. He proved a generalization of Turan's theorem. So Turan's theorem says if I forbid a clique of size r plus 1, then the maximum number of edges I can have are in some complete r-partite graph. So namely, the balanced complete r-partite graph, the Turan graph, maximizes number of edges. And then Erdős proved that, again, we are going to forbid kr plus 1. Then also, Turan graph maximizes the number of cliques, so ks of any size. That makes sense. Okay. Right, so in this case, we have like the same extremal examples for both number of edges and number of cliques. But that's not always the case. Okay, and then there have been many other results. I didn't include more, some results using flag algebras and many other methods. And so something else I didn't include, there's some applications for this type of generalized extremal problems in graphs to hypergraphs as well. Okay. And it's also related to this subgraph density problem, which is also quite popular recently. Okay. So for simplicity, let's define this function ngt to just be the number of unlabeled copies of t and g. So I want to restate the Erdős theorem that we mentioned earlier. So recall if we have some non-Hamiltonian graph with minimum degree at least some value d, then the maximum number of edges we can have is whatever the maximum of this h and d, or h in floor of n minus 1 over 2. So you can check using calculus that this function h and d is bigger than the other function whenever n is large compared to d, at least 60. So we can restate the theorem as, so for n at least 60, g is an n-vertex non-Hamiltonian graph, minimum degree at least d. Then, so ng k2, maximum number of edges, number of edges in G is at most in H and D K2. So the number of edges in our extremal example, H and D. Okay. So here's the same thing, just copied over. And the first new result I want to talk about today is a generalization of this result, which says, so now I'm going to fix any graph I want T. This is the graph I want to count. And I let n be large enough compared to T and whatever D is. Then G is an in-vertex non-Hamiltonian graph with minimum degree at least D. Then the number of copies of T and G is at most the number of copies of T and H and D. So again, it's kind of like the Erdős generalization of the Turon. We have this extremal example that maximizes the number of edges, but in fact, it maximizes the number of copy of any subgraph, as long as n is large enough. Okay, any questions? So, right, so n needs to be large enough, and we have this bound and not for how big n should be for this proof to go through. So it's 4dt plus 3d squared plus 5t. We believe it's probably not best possible. I mean, at least like, okay, we don't care about the constants, but the order is probably not best possible. And we think the correct order is dt. Okay, so here's an example. You take t, which is the graph you want to count, to be the star on little t vertices. So we have t minus 1 leaf vertices, and choose n to be at most dt minus t. Then our extremal example, h and d, is not going to maximize the number of stars. So that means we're able to find some non-Hamiltonian graph, minimum degree at least d, which contains more copies of this star than h and d does. So namely this, actually the other end of the extremal examples, hn floor of n minus 1 over 2. So here we have a larger independent set and a smaller clique here, but we have many edges here, a large complete bipartite subgraph, and there we're going to pick up many copies of stars. Okay. So it's still open, if you want, to try to get rid of this d squared term for whenever d is large compared to t. Okay, and then just as a simple corollary, so I dropped the minimum degree condition, just want to look at non-Hamiltonian graphs. Then for any t, for n large enough compared to t, so this x and t cn, maximum number of copies of t in a graph without Hamiltonian cycle is the number of copies in hn1. So this was our first extremal example. Okay. So in general, it's kind of hard if you have some arbitrary t to calculate the number of copies, the number of embeddings of t into some host graph. But in the case where t is a fairly nice graph, we can get some stronger results. So for example, let's count the number of cliques inside our non-Hamiltonian graphs. So, okay, so for k, r integers, the number of copies of kr in our h and k graph. So we have some clique of order n minus k. So we can get n minus k choose r from there. We have k vertices with degree exactly k. And each one of those are in k choose r minus 1 r cliques. Okay, so this is the exact number. And so again, this function is convex in k. So it's actually decreasing for most of the time as k is increasing. Okay, so for cliques, not only do we have this counting theorem, we also have a stability theorem. So we're going to fix d, we're going to fix r is the size of our cliques, choose n to be large enough. Then if G is an n-vertex non-Hamiltonian graph with minimum degree at least D, and the number of R cliques in G is greater than the number of R cliques in H and D plus 1, then what can happen? G is either a subgraph of H and D, so our first example, or G is a subgraph of this new graph K prime ND. So here we have a clique of order n minus d, another clique of order d plus 1, and they share one vertex. Okay, so let's dissect what this is actually talking about. So first of all, for this n large enough, we can calculate n exactly, but it's kind of messy. So I just chose not to include that. So n is not a problem. So this is saying that for every non-Hamiltonian graph, minimum degree at least d, that is very dense by this definition of dense, all it can be is, or it has to look like one of these two examples. But not only does it have to look close to these examples, it has to be exactly contained in one of them. So the best we can do is just start with one of these and throw away some edges. Okay? And then also, so if we only care about two connected graphs, because every Hamiltonian graph has to be two connected, then we cannot be contained in here. So really, this is the only thing that we can resemble. Okay, so this gives us a classification of every very, very dense non-Hamiltonian graph that meets the minimum degree condition. Okay, and then so we might want to, do another step of this classification. But if we allow, so what happens if we allow less dense graphs? Hamiltonicity is a property of having many edges or many cliques. So if we allow fewer edges or cliques, then we should have many different types of non-Hamiltonian graphs. So we have this threshold for a number of cliques or number of edges, whatever you want. And if we make the threshold too low, then we should expect lots of different graphs, so we can't get a great classification. But we can try to be a little bit modest. So what if we allow graphs with more than, so h and d plus 2, or more cliques than h and d plus 2 has, then what do our graphs look like? So let's look at the extremal examples. We can still have these two old extremal examples. We might also have the case where instead of h and d, we have now h and d plus 1, or k prime nd plus 1. So grow each of these blobs by 1. And then if you think for a while, you might come up with this third graph. So I called it h prime nd. It's composed of the set of d plus 1 vertices, which have only one edge amongst them. And each of these vertices have the same d neighbors inside this big clique. Okay, so all the blue subgraphs are cliques. And so if we contract this single edge here, then we go back to this first family of graphs. Okay, so those are three types of families that our graph can be contained in. So the extremal example, we also take all very dense subgraphs of those. And so we ask, can there be more container graphs? Not like containers, but you know what I mean. And the answer is, most of the time, no. Okay, so here is a more precise statement. So again, fix D and R large enough. G is an in-vertex graph with minimum degree at least D, such that we have many, many R cliques. Then G is a subgraph of one of the following graphs. So it can be in one of these three families that we just talked about. And there's only two bad cases for specific values of D. So the first bad case is this Fn2 graph. So here we cannot include all three of these vertices in a Hamiltonian cycle. Or if D is equal to 3, then we have this other example. Okay, and so everywhere where D is at least 4, it's nicely behaved. We just belong to one of these graphs. Okay, so maybe we might think that these two bad examples would generalize to larger D, and they do, but the way they generalize, they become Hamiltonian, so we throw away those cases. And so one last comment. So what now we have here is, in this class of very dense graphs, Hamiltonian graphs, non-Hamiltonian graphs, we have an exact classification. Okay, so you can check that if I have a graph with at least this many arc leaks, so maybe it would be easier to just consider edges because it's easier to calculate number of edges. I can actually write a polynomial time algorithm for each of these graphs to check if that graph is contained in them. Okay, so what this gives us is a polynomial time algorithm to check Hamiltonicity for very dense graphs. Okay, and that's all I want to say. Thank you.